Acids and Bases Part 1. Introduction to Acids and Bases, Definitions, and Molarity. Making solutions. To move the solvent next to the solute, you have to stir. After stirring, the solvent should touch the solute, which makes it dissolve. The smaller the pieces, the more surface area of the solute. To speed up the rate of solution, you can move it, like stirring or shaking. You can make the particles smaller, and you can increase the temperature of the solution. High temperatures cause the solvent molecules to move faster and to touch the surface more times and to hit it harder. The rate of dissolving to speed up and the amount that's dissolving to increase, except for gases, which actually is opposite. Alright, so for solutions, you need to know these definitions. First, solubility is the amount that a substance will dissolve at a specific temperature, and it is measured by grams of solute per 100 grams of solvent. Okay, the next one you need to know is saturated, which is the maximum amount of solute that is dissolved. For an unsaturated solution, you are able to dissolve solute, but it's less than a saturated solution. For supersaturated, to get a supersaturated solution, you have to increase the temperature, and it actually holds more than it's expected to hold, and it dissolves more than a saturated solution. For polar and nonpolar, polar solutes will only dissolve with the polar solvents, and nonpolar solutes will only dissolve in the nonpolar solvents. So, if you put a polar solute in a nonpolar solvent, it will not dissolve. The purpose for the solute and the solvent is it will actually tell you if the substance will dissolve and how much it will dissolve. The solute must always be added to the solvent, so the solvent can never be added to the solute because it will not dissolve. To find molarity, you can use this formula that's on the screen, and it's moles of solute over liters of solvent. Okay, so for our first molarity example, the question is, what is the molarity of a solution that contains 0.456 moles sodium chloride in an 8.76 liter solution? So you plug in your numbers to the formula, moles over liters, and you come out with 0.05. For this example, you have to convert grams to moles, so you do 435 grams of hydrochloric acid times 1 mole divided by the molar mass of hydrochloric acid, and you come up with about 11.9. Okay, for the last example, it's how many moles are in a 3-liter solution with a molarity of 0.25, so it's a little different because it gives you the molarity and you're looking for moles, so you plug it in and you get about 0.75 moles.
Acids and Bases Part 2. Theories. The Bronsted-Lowry theory. Acids demonstrate a proton in the form of a hydrogen ion. Bases accept a proton in the form of hydrogen ions. You can see an example of this below. How to identify acids and bases. To identify a conjugate acid, you identify what is left after the base accepts the proton. To identify a conjugate base, you identify what is left after the acid donates a proton. Here are some examples. Try to identify the conjugate acids and the conjugate bases in both equations. Next is amphoteric compounds. This type of compound is any compound that is either an acid or a base or has the potential to be one. Water is the quintessential amphoteric compound. Next is the Lewis theory of acids and bases. Based on this theory, acids accept an electron pair from a base, while the bases donate the electron pair to the acid that is accepting it. Next is Arrhenius acids and bases. According to this theory, acids increase the hydrogen concentration in a solution. However, the bases increase the hydroxide concentration within a solution. Next, we have Henry's law. According to Henry's law, the pressure of the gas above the liquid is directly proportional to the solubility of a gas within a liquid. Second to last, we have indicators. An indicator is any type of compound with a pH-sensitive color. Its transition level is the range of pH that an indicator works. Last, we have titration. A titration is how you determine the pH of an unknown solution by using pH of a known solution.
Acids and bases, Part 3, Properties. Properties of acids and bases. Acids taste sour and react with metals to make hydrogen gas. They also react with bases to make water and salt. They conduct electricity, and the litmus paper will change from blue to red, and they contain hydrogen ions. Bases taste bitter, and they will feel slippery or soapy when you touch them. They react with acids to make water and salt. The litmus paper will change from red to blue, and they contain hydroxide. Some common acids and bases are milk, soda, distilled water, acid rain, stomach acid, and carbon dioxide. And some bases would be blood, antacid, ammonia, Drano, and egg whites. And you'll notice they are all common things, not just found in a lab. So for a recall, ionization means the process of converting an atom or molecule into an ion by adding or subtracting particles. And when you add an acid or base, it will increase the ionization of water. Now we're going to talk about strong versus weak. A weak one would only ionize partly, and the arrows could go both ways because the reaction could go either way. And an example of this would be acetic acid. A strong one will completely ionize, but the arrows can only go one way because the reaction can only go one way, and there is an example of a strong one. Now we all know our prefixes such as mono is one and di is true, so a monoprotic acid can only give away one proton. An example of this would be nitric acid. So a diprotic can only give away 2 protons, and a triprotic can only give away 3 protons, and there's an example of all 3 of these below. You should also know that protons are given away in steps. They won't be given away all at one time, but over a period of time.
Acids and bases, Part 4, pH and pOH. We'll start off by talking about the self-ionization of water. This happens when 2 water molecules react with each other to make 1 part hydronium and 1 part hydroxide. This is extremely rare and only happens every 1 to 10 trillion. Now to talk about the pH chart. You read the chart vertically from top to bottom and bottom to top. In this specific chart, the strong bases would be on the bottom at a range of 10.1 to 14. The weak bases would be between 7.1 and 10. The neutral solution is always 7. A strong acid is between 0 and 3.9, and a weak acid would be between 4 and 6.9. Besides pH, there is also pOH. pH measures the acidity of a solution, and the lower the pH, the more acidic it is, while pOH measures the basicity, which is how basic a solution is. The lower the pOH, the more basic the solution will be. When added together, pH plus pOH will always equal 14, which will help you in conversion factors between the two. Here we have an extremely handy conversion chart that will help you to convert between a hydrogen ion, hydroxide ion, pOH, and pH. Now for example, if you were to convert from pOH to pH, you simply follow the arrow from the bottom right to the bottom left and use the equation pH equals 14 minus pOH. Plug in your variables and there you go. It's as simple as that. Now we can work through some practice problems. If the pH of a solution is 5.4, what is the hydrogen ion concentration? Now very simply, we know that we're going from pH to the hydrogen ion concentration, so we know that we'll be using the formula hydrogen ion concentration equals 10 to the negative pH. Here again we have our equation, and it is as simple as plugging in the variables to the correct positions in the equation. So putting the negative pH is equal to 5.4 and plugging it into the calculator. Problem 2. If the pOH of a solution is 10.9, what is the hydroxide ion concentration? Again, we'll be using our conversion chart to solve this problem. We'll be going from POH to hydroxide ion concentration, and we'll use the equation hydroxide ion concentration equals 10 to the negative POH. This problem is as simple as the last. You simply take the variables and plug them in. So the negative POH goes as the exponent to 10, and you plug that into the calculator and you'll find 1.26 times 10 to the negative 11th as your hydroxide ion concentration. Here's our final problem. If the hydrogen ion concentration is 8.4 times 10 to the negative 7, what is the POH of the solution? Here again we have our conversion chart, and this time we'll actually have to use two separate equations because we'll be going from the hydrogen ion concentration to pH to POH. First, we'll use the pH equals negative log of hydrogen ion concentration, and then from there we'll convert the pH to the POH by subtracting the pH. Here you just plug in your variables. The hydrogen ion concentration is given at 8.4 times 10 to the negative 7, and when you plug that into the calculator, you'll get around 6.08. But you're still not done because you have to convert it to POH, and to do this, you take 6.08 and subtract that from 14, and there's your answer.